for this thing. But I can't help but notice, just looking out on the crowd right now, nobody is shaking. Not a quake, we're all kind of standing still, we're just looking at it. But if you look really closely, you can see the symphony of movements and the tiny motions of the cells and the changes of pressure and everything. You would be quaking with all. Because all this stuff, it's so cool, it's beautiful. This pinnacle of evolution, this pea plant, is something that we need to appreciate more, but are denied that capacity to appreciate more because the scales at which we human beings have evolved to sense things are not the same scales on which this plant, most plants, are behaving. The movements and these symphonies of form are not on that scale at which we typically appreciate things. Not at the scale of the animals that we were evolved to hunt or necessarily moving around and that kind of thing. So, what we in the Plant Pulse group are soon presenting is a strategy and a couple attempts at developing strategies to amplify some of this movement and have some approaches to really get at a plant and bring that scale to something sensible to our species. So, we're getting into mix here. Now, we can start, while the slides are coming up, with a mirror. We're going to use this mirror as an optical lever to amplify this movement to that scale. Okay, next slide. You go.
Yep.
Okay, so we took inspiration from Bose's Cresco graph, which essentially tried to see how much a plant moved by amplifying it. I'm not exactly sure how it worked. It used some sort of like smoke and laser, like etch and sketch mechanism, but we used we were the ones that used the laser.
Yes.
By taking advantage of...
Lasers were not invented at that time. This is 1850s.
I'm sure you forget.
Yeah.
We used similar triangles to take advantage. We took advantage of similar triangles to sort of amplify the motion of the plant. As Jack was mentioning, we used a mirror to project the laser onto a farther screen.
Yeah. On the left here, you see Bose's kind of original design from the early 20th century, I believe, where he used a system of levers, where you see here the plant connected near the start of this lever, near the pivot here, a series of levers to amplify the motion, the growth of the plant, about 10,000 fold. He records that on just smoked glass here. Now,
So literally smoke and mirrors.
yes, literally smoke and mirrors.
The history of smoke glass comes from the fact that we didn't have any graphing devices. So if you have a little scribe and you take smoke's glass, you make a line and a scratch in it. So it's graphing, original graphing paper.
And our strategy, sorry, go ahead.
Oh, so this was our first attempt. Wait, you can do. You'll hear Jack's beautiful voice. Well, only slightly. Essentially, it was just like a proof of concept to say like, oh, we can make a string. If we tug on it, it'll move the mirror and project it and amplify motion. But the problem was that it wasn't sensitive at all, so it wouldn't show plant growth at the scale we needed it to. So what did we need to in order to actually sense the growth of the plant? Well, we needed to amplify it 10,000 times because apparently our attention span is only 10 seconds. And plants, like, a fast plant would grow like 3 centimeters per day. So doing a little bit of math, and you get a desired amplification of 10,000 times.
Yeah, which is determined by that B over A equation, where you're really just trying to optimize that distance between the mirror and the wall. Right, and before we get into the future iterations, I wanted to talk about a couple things that we tried that didn't work. The first that we had kind of talked about in class, and the first was trying to use Mylar instead of a mirror because decreasing the weight of the mirror component would help make the measurements more seamless. And so I actually went to the Stanford Educational Farm and asked them if they had any Mylar at Kevin's recommendation. And they did. They had a big wheel of it and they let me take a cut of it. And we tried that in our designs. But as you can see, there were imperfections in the Mylar that resulted in the point not being very accurate. And so we decided ultimately just to stay with the mirror for our designs. But I think switching to something like a like more perfect but thin material like that would be good in future iterations. And then we also talked about the glitter disco ball in class a little bit, and so we gave that a try as well. And definitely you can see that the laser reflects off of the glitter and it's very pretty. But even in a dark room, we weren't able to get a reflection that was up onto the ceiling that gave that dramatic disco ball appearance where you could see movement from the plants. And so I think maybe this could be iterated on, but we ultimately decided to move away from it.
Yeah, so next we kind of had a V2, another iteration of the Crescograph with our laser. So we made some 3D prints to hold up a pen as a rotating mechanism, which then attaches to the plant with a little string there. And then there's a mirror, you point the laser at the mirror and then you can see the reflection on the whiteboard. This was kind of a larger scale try to see if we could amplify more than just in the first box. So this is kind of what it looks like with a little bit of movement. You can see there's a lot of movement on that end. This was really good because it showed that we could actually amplify the laser movement and the plant movement more accurately. We were able to kind of by coincidence see that there's a lot of less vibration on these desks just because we think the wheels are rubber, and that probably helps a lot with like damping of everyone walking around and stuff like that. And then this kind of paved the way for our next experiment, which we'll talk about. The challenges that we wanted to improve upon were, you can kind of see, but the pen was like kind of hard to balance on these supports, and we taped everything together on the pen with the mirror, which is like super frugal. I mean, it worked, but obviously there's ways to improve that we wanted to do for the next one.
So our next approach was to start reducing some of the other degrees of freedom for our little mechanism here, for our rotating mirror that's allowing us to amplify some of this motion. So Bose was using these delicate pivots. We were confident with our Play-Doh and tape and shaky hand strategy, we wouldn't be able to be quite as delicate. Our other goal is to use this sort of in a classroom setting where things might need to be a little robust. So we opted just for doing things with some ball bearings which are reducing motion to that single rotational degree of freedom. Now we'll talk a bit about remaining friction in a ball bearing setup, but for now we'll just look at this, the setup we have so far, where we have our rotating mirror between two bearings, and that's standing over our P plant there between between the tables there. Now, over on the other side of the mirror, there in the distance in this image is the actual board, that board that we are projecting onto, where we have a distance from the mirror of about 6 meters. So from there to there is about 6 meters. Now, from the string where the plant is actually attached to the axis of the mirror where it's rotating is about 1 centimeter. Now, that yields an amplification of the motion of about 600-fold. So if we go to the next slide, and then we watch what happens to this mirror clip to the plant over about an hour and a half, we see it moves because the plant grew. So unfortunately,
Was it going in the right direction?
yes,
Yeah.
it actually
Yeah,
was.
that's
Yes,
right.
okay, good.
Plant is not degrowing.
The plant is not ungrown yet. Sorry. So it grew, or some other component moved. But we're saying the plant grew. That's very exciting. Now,
We
admittedly,
can prove it later.
admittedly, the average person, I certainly don't have a 90-minute attention span. So while it would have been very cool to be staring at that very carefully for 90 minutes straight, we of course used a camera and then sped it up later. So we're gonna need to amplify this more, essentially. We're gonna need to get closer to the realm of 10,000 times magnification that Bose had in his original press script. But for now, I think this is a nice place for us to reach so far.
Yeah, I think another thing is just based on, how much we moved, each dot for reference is about 1 inch. And so back calculating, we saw it grew about 0.3 millimeters, which we thought was also reasonable.
That
for
is
the time span.
absolutely phenomenal. Actually, this is a reasonable number, so I'm
Yeah.
now convinced that it.
Yeah, we were impressed by that.
Press play plan. Actually, it's also funny that the growth is not linear. I kind of see it.
Yeah, it's like kind of jumps a little
Yeah,
bit.
it jumps, which is also, I mean, it could arrive from the static friction in the bearing, but it could also be growth is not a linear parameter. So when you differentiate that signal, you would see patterns.
Yeah, and so with more time we want to amplify the growth to be even faster. Some ways we could do that is making the string more rigid. There's also some friction with the mirror and the 3D printed part with the tape. So working to remove some of that friction. We can also increase the distance between the wall and the laser to be able to see that faster. And then the quantitative part is also very important. So maybe getting something like photosensitive paper and creating a graph with laser height over time. And then we really want to bring this into classrooms, and our target audience is high school students. So creating some sort of lesson plan on plant growth with optics as well, and being able to teach this. Thank you so much.
Don't get off the hook until we choose. When are you going into a classroom? I think you have sufficient material to walk into a class.
I'll bring it to summer camp in 3
Yeah.
weeks.
Okay, yeah, no, I think I really mean it. I'm not gonna
Yeah.
give you guys a grade. In a class. Okay, question, one quick question. Go ahead, and then Ching, 2 quick questions. 10,000.
Yeah.
Yeah, so the setup as kind of drawn with those 2 similar triangles that the mirror is forming, you get the magnification is equal to the distance from the plant's attachment to the axis of rotation here, versus divided the ratio of that distance to the distance from that axis to the actual board that you're on. So if you wanted 10,000 fold amplification, if this was 1 millimeter away here, you would need the board to be about 10 meters away on the other side there. The actual one we had was 1 centimeter here, just based on how we made it, and 6 meters there. So somewhat less than we need, only 600.
But you know, 60 meters. Pretty easy.
Yeah.
Field to do. I mean, optics, lasers, you use them as guide stars up in the sky.
Yeah.
This is the beauty of lasers, that they don't differentiate. Fairly easy to align laser. Quick question. The light interfering with the growth or no? No, but the light is not shining on the plant. The light is shining on the mirror, which is
Yeah.
mechanically coupled to the plant, completely isolated. There's a coupling between the what's happening in the tension. The plant is tugging on the mirror far away. That's correct. Yeah. In the glitter ball example, light will be shining on the plant. Yeah, yeah.
One thing you could do with the whiteboard, instead of having it flat, if you have it tilted, you can detect it's like how shadows move faster during sunset.
Oh, that's a cool
Yeah.
idea.
Yeah. There's lots of ways. Optical amplification works just like levers. So there's lots of clever ways of tilting. Double tilt will do the trick. When you have the light bounce back at the same mirror again, you do all kinds of, just like he both folded his thing. There was 2 pivots. And so there is a double amplification. So this doesn't have to be. Okay, time's out. Awesome. I have to say special shout out for the opening.
That's the camp counselor I know.
Said you need to be in the classroom. Okay, switch. Who's going next?
Remember to be on the
Anyone-
Zoom if you're presenting.